Imagine embarking on a journey aboard a spaceship, heading in one direction as far as possible from Earth. Now imagine that the spaceship can constantly accelerate up to the speed of light, and you have an infinite lifespan. How long would it take you to reach the edge of the universe? What would it look like? How would you cross it? And if you were to cross it, what would be beyond? Does the universe have an edge, or is it infinite? And what shape does our universe have? In this video, you'll find out the answers to these exciting questions about the boundaries and shape of our mysterious universe. What lies beyond the edge of the universe? Please leave a thumbs up. It shows YouTube's algorithms that this video is interesting and worth watching. It's 2023. An article published in Nature introduces a bewildering discovery by the new James Webb Space Observatory of 6 celestial objects that simply shouldn't exist. 13.8 billion years have passed since the Big Bang. Yet, these objects formed just 600 million years after it, in the nascent universe. We're talking about 6 galaxies, and notably, very massive ones. No one can wrap their head around the fact that such giants could have formed so early in the universe. Existing models suggest that these galaxies should be at least 10 times smaller, if not 50. According to calculations, there simply should not have been enough ordinary matter, the substance that comprises stars, planets, and ourselves, available at that time to form so many stars so quickly. If these findings are confirmed, we'll face an unsettling realization that we've been wrong all along. The widely accepted figure of the universe being 13.8 billion years old might be incorrect. In truth, the universe could almost be twice that age, an astonishing 26.7 billion years old. And this is not another amusing scientific oddity like, well, we didn't know this fact, but now we do, so good for us. This one genuinely has some profound implications. One of the study authors, Erica Nelson, said, if even one of these galaxies is real, it will push against the limits of our understanding of cosmology. For now, there are no explanations for this anomaly, but wry suggestions for the concept of dark time that expedites the development of cosmic structures have already surfaced in discussions. Indeed, if all of this is confirmed, and it's not about the perfection of our observation methods, and no mistakes have been made, it will signify a crisis for our theoretical understanding of space. Despite our incomplete understanding of the universe's dimensions, we can assume that it does have some, however vague they might be. And if the universe has boundaries, then we could theoretically reach them, right? So what would they look like? Let's do a thought experiment to figure this out. Suppose we venture towards any point in the celestial sphere. Will this movement ever have an endpoint? And if so, what would it look like? Would we run into a black wall? Or perhaps pass through it? And if we did, where would we end up? For those who deem such speculations naive or even childish, it's worth noting that this question has perplexed humanity for millennia. A significant part of our past cosmology focused on the center and the edge of the universe. For instance, a 19th century engraving represents how medieval people imagined the boundary of the universe, beyond which lies the mechanism governing the cosmos. Admittedly, we haven't yet arrived at a definitive answer to this question. Today, we'll explore several of the most plausible theories. Please stay tuned for the end of the video, where we'll talk about the closest, most obvious, yet most elusive boundary. First, let's revisit some crucial points. If we were to take a powerful telescope and try to explore deep space, we wouldn't see the edge of the universe, but rather its hypothetical beginning. It's widely understood that when observing a person at the next table, we see them as they were 3 nanoseconds ago. But looking at the star Betelgeuse, we see it as it was 500,000 years ago. But it could have already exploded by now. Gravity works similarly. We perceive the sun as it was 8 minutes and 20 seconds ago, and our planet is gravitationally drawn not to the current location of the sun, but to where it was the very same 8 minutes and 20 seconds ago. And if the sun suddenly vanished without a trace, the Earth and other planets would continue orbiting an empty space before eventually scattering in different directions. For the same reason, Andromeda Galaxy, the largest galaxy in our local cluster, which is heading straight towards us at approximately 400,000 kilometers per hour, is really about 900 light-years closer than it appears. 900 light-years is a lot. To put this into perspective, the closest star to the Sun lies 4.24 light-years away from it. But even with modern technology, it would take tens of thousands of years to reach it. In general, you get the idea, right? You can't just look at something and see it in real time. The farthest we can observe is the point from which light has had time to reach us since the Big Bang. The closest such point is over 46 billion light-years away. So immediately there comes a question of how this can be, considering the universe is only 13.8 billion years old. Are objects beyond this distance relics predating the birth of the universe? No, of course not. It's all about dark energy and the rapid expansion of the universe it provokes. It's not that the light from the most distant objects has reached us, but rather space itself has expanded so much that we can see much further than the universe's age. Specifically, those same 46 billion light-years in one direction. This is the boundary of the observable universe. While intriguing, it's not our primary focus, because it's almost certain that space extends beyond this boundary. However, we are seeking the real border, not just the visible one. First, let's try to tackle the problem head-on by asking the question, what would happen if we took a group of people, put them in a spaceship, and sent it in one direction in an attempt to reach the edge of the universe, considering that they would fly as fast as possible? David Kipping, an astronomer at Columbia University, has answered this question in the most detailed and intriguing way. Imagine that a spaceship can accelerate indefinitely at a rate of 10 meters per second squared. Why this particular rate? Besides the steady acceleration, this would make passengers feel as if they were experiencing normal Earth gravity. The ship's bottom would push the crew with the same effect as the Earth's gravitation. Now, let's keep in mind that the freefall acceleration on Earth is 9.8 meters per second squared. But we round it up to 10 to make the calculations easier. Everything's clear, right? In the first second, the ship will travel at a speed of 10 meters per second. In the second, 20 meters per second. In the third, 30 meters per second, and so forth. After an hour, the speed will reach 35,280 meters per second and continue to increase by 10 meters per second squared. After 2.5 hours, the ship would whiz past the moon. After a week, past Saturn. 11 days in, it would fly past Neptune, the farthest planet in our solar system. For the sake of this thought experiment, let's dismiss practical concerns such as fuel supply and potential catastrophic collisions with cosmic dust. After 15 months of travel, the spaceship would have covered its first light year. At this point, its tremendous speed would already cause unusual phenomena due to the increasing influence of Einstein's special theory of relativity. At first, nothing prevents the spaceship from accelerating indefinitely, but a massive object like a ship cannot reach the speed of light. It can come as close as possible, but never reach it. For example, protons in the Large Hadron Collider are accelerated to a speed of 299,792,455 meters per second. It may seem like a mere additional 3 meters per second would be enough to reach the speed of light. 3 meters per second is an average jogging pace. But actually, no. Even if you spent all the energy in the universe to accelerate the proton by a measly 3 meters per second, it would only approach the speed of light incredibly closely, but wouldn't reach it. If not for this limitation, the spaceship would have surpassed the speed of light within 45 days. But something different happens in reality. The special theory of relativity postulates that the faster we move in space, the slower we progress in time. Therefore, some counterintuitive phenomena would happen in this situation. As the spaceship's speed approaches the limit, an outside observer would perceive the ship's speed as decreasing, with the onboard crew moving as if in slow motion. But from the perspective of the people on the ship, time would go as usual, and the acceleration would remain constant at 10 meters per second squared. Moreover, it would seem to the people on the ship that time outside the ship has sped up. Again, if not for the laws of the special theory of relativity, the ship would have exceeded the speed of light in 45 days. But in actuality, after 15 months of flight, it will only be moving at 87% of light speed. As the spaceship approaches the speed limit, time doesn't slow down evenly, but like this. That is, even when accelerating to half the speed of light, you almost wouldn't notice the time slowdown. When you reach 90% of the speed of light, time only slows down about twice. The extreme slowdown only begins when you closely approach the speed of light. For example, on October 15, 1991, a space particle named Oh My God reached us. It remains unclear what this particle was, but it got its name because its energy was equivalent to the energy of a baseball moving at a speed of 93.6 kilometers per hour. Just think about it. That's the energy of a single particle. This particle moved at a speed that was this percent of the speed of light. 99.999 several times over 51%. Scientists are yet to comprehend what propelled this particle and made it move at such a mind-boggling speed. Recent studies using the telescope array project have suggested that the source is in a 20-degree zone in the direction of the Ursa Major constellation. That's all we know so far. But it's scary even to imagine what it might be. The most amazing thing was that for this particle, the time slowed down. Just think about it. By a factor of 300 billion compared to a stationary observer. This means that while it would have taken 2.5 million years for us, the stationary observers, to travel from the Andromeda galaxy, the particle would have perceived it as less than 5 minutes. This means that time completely stops for light itself. The principle is clear, right? But the dramatic divergence in the time rates of our spaceship crew and the rest of the universe is only part of the problem. If the ship doesn't return, but just keeps flying, then after passing the 8.3 billion light-year threshold, there would be no coming back. Now this is truly amazing. Why? After all, there isn't any physical boundary there. But as soon as you pass the 8.3 billion light-year mark, that's it. You're trapped. Due to the expansion of space, the casual link with the solar system would be broken, and no amount of acceleration would ever allow you to return to its vicinity. This is all because the area of space where you are is moving away from Earth faster than the speed of light. It's not that you are moving faster than the speed of light, but that section of space itself. There are no violations of the laws of physics here because we are talking about space itself, not objects within it. An easy way to understand this is by picturing a slinky toy. If you stretch the slinky, you'll notice that each of its coils only moves a finger's width away from its neighbor, which is quite slow. However, during the same period, 2 coils at opposite ends of the slinky move over a meter away from each other. The same principle applies to galaxies in the universe. Due to this mechanism, distant galaxies can move away from us at the speed of light, or even faster. The same would happen to you if you fly far enough away from Earth. You would go beyond the edge to an area that's moving away faster than the speed of light. If you then decided to return to Earth, turn your spaceship around, and fire up all the engines, you'd still be moving away faster than you're approaching. It's terrifying even to think about the hopelessness that awaits the spaceship's crew. But that's only part of the story. An even more daunting reality awaits the crew. We need to take a step back to understand this. Remember, we said that due to dark energy and the expansion of the universe, our visual reach isn't limited to 13.8 billion light-years, but extends a full 46 billion light-years in one direction. And that's just for now. As space continues to expand in the future, this visible sphere will also expand, but only to a certain limit. Based on calculations, scientists estimate that our future vision limit will expand about 33% beyond the current limit, specifically reaching about 61 billion light-years away. This is the maximum limit to which, and we can't stress this enough, our visible universe can expand. However, being visible doesn't mean it's reachable. Dark energy, this powerful and yet incomprehensible force, has literally divided the universe into concentric regions. At a distance of less than 15 billion light-years, there are 66 billion galaxies. Theoretically, the galaxies within these limits are reachable to us. The crew of our hypothetical spaceship could reach them if it were moving at the speed of light. And someday in the future, Earthlings will be able to see these galaxies as they are right now at this very moment. The area that lies from 15 to 46 billion light-years away contains about 2 trillion galaxies. At such a distance, we'll always be able to see them, but for us, their age will never reach 13.8 billion years, and we'll never see these galaxies as they are today. They are beyond our reach, even if we could travel at the speed of light. If we were to observe them for tens of billions of years, we wouldn't see any development. For us, they will always remain as frozen, motionless farewell photos, slowly fading away until vanishing completely. Galaxies at distances from 46 to 61 billion light-years are currently invisible to us, but future generations will see them when their light from the past finally reaches us. However, these galaxies are already unreachable, even on a spacecraft traveling at nearly the speed of light. Galaxies lying beyond 61 billion light-years away cannot be seen or reached by us or anyone else, even in the most distant future. We've never seen them and have no idea what is happening there. Please keep in mind that we are not talking about some distant future, but what is really happening right now. For instance, consider the galaxy GN-Z11. This is one of the most distant galaxies we know today. Its age is 13.4 billion years, meaning its light was emitted 400 million years after the Big Bang. It's located at a distance of 32 billion light-years from us. We can still see it, but what we see is a farewell photo. The image of the galaxy GN-Z11 will slowly fade until it eventually vanishes forever. Because, as you understand, the light this galaxy is emitting right now will never reach us, unless of course the expansion slows down again. Right now, the galaxy GN-Z11 is moving away from us at a speed of 687,000 kilometers per second, over twice the speed of light. Unfortunately, this is exactly where the sad conclusions begin. The fact is that it goes far beyond GN-Z11. Think about it. More than 96.7% of the galaxies we can observe today have already vanished. The light they emit right now will never reach us. 98.6% of the galaxies we will ever observe have already disappeared. In other words, we are theoretically set to see a total of 4,700,000,000,000 galaxies. However, 4,634,000,000,000 of these are already beyond what we can reach, even if we could travel to them at the speed of light. And only about 66 billion galaxies still remain within our reach today. And please note that this is only a current estimate. This problem will only get worse over time. Right now, if we assume that each of the 66 billion galaxies has as many stars as the Milky Way, which is about 400 billion, it means that roughly 60,000 stars are disappearing from our field of view every single second. Tens of millions of stars have already disappeared since the beginning of this video. We'll continue to see their past light for billions of years, but any new light they generate from this very moment will never reach us again. Of course, they don't disappear in the full sense of the word. They continue to exist, just somewhere beyond our reach. But what difference does it make to us? We are no longer casually connected to these objects. Regardless of what we do from this moment on, we can't influence them anymore, nor can they influence us. Any information about these places is now fundamentally unattainable to us. For us, they simply cease to exist. If the force of space expansion can never overcome the gravitational force within galaxies, then gradually each of them will slowly sink into a complete darkness and solitude. Over time, existing stars will burn out, particles will decay, black holes will evaporate due to Hawking radiation, and the universe will be just empty space with only dark energy, ensuring its exponential expansion for eternity. Keep in mind that dark energy is kind of the opposite of gravity. That is, the more matter the space has, the stronger the gravitational force. Conversely, the emptier the space, the stronger the dark energy. As counterintuitive and odd as it may seem, its density per cubic meter doesn't decrease with the expansion of space. So do you see what is happening here? As the expansion of the universe accelerates, there will be more and more empty space, which will, in turn, accelerate the expansion process, resulting in even more empty space, and so on for infinity. Events in one part of the universe won't be able to affect what's happening in others. After all, going back to our previous point, the universe will be nothing more than an empty space, filled only with dark energy, making it expand exponentially. And now is a good time to go back to our imaginary spaceship. So what would happen if the crew kept flying at nearly the speed of light? By the time the onboard clock would strike the 200th year of the journey, 10 to the power of 41 years would have passed in the rest of the universe. That's 1 with 41 zeros. Due to the expansion of space, at this stage, it's statistically likely that there are no other particles within the observable universe aside from the ship itself. The spaceship would be traveling through a pitch-dark universe. Well, we can consider the first thought experiment to reach the boundaries of the universe unsuccessful. The universe would end faster than we could reach any hypothetical edge. But this is just the beginning. We're making these assumptions based on the premise that the universe is flat. Wait a minute. What? It's enough that we are puzzled by the theories of a flat Earth, and now a flat universe too? Luckily, it's a whole different story. To understand this, we need to delve deeper into the question, where is the edge of the universe? And does it exist at all? First of all, what makes us think that the universe, whatever it is, has any sort of boundary at all? Could it really be infinite? The javelin argument is an ancient logical argument put forward by the Greek philosopher Archytas to prove that the universe is supposed to be infinite. It goes as follows. What happens to a javelin when it is thrown over the outer edge of the universe? Will the javelin rebound? Or will it pass through and out of this world? If it passes through, then is there something else beyond the edge? If it rebounds, then the javelin is constrained by a certain barrier. But that barrier must also be constrained by something. And the thing that constrains the barrier must also be constrained by something, and so on to infinity. Hence, the universe is infinite. For more than 2,000 years, the most talented minds worked on this riddle, and it is safe to say that the riddle of Archytas has largely influenced the history of cosmology. However, what the ancients didn't realize was the possibility that the universe could be infinite and yet have edges. How could it be? We need to look a bit from afar off here. Everyone knows that the sum of the angles of any triangle is 180 degrees, but that's not really true. Back in the 19th century, one of the greatest mathematicians in history, Carl Friedrich Gauss, began to suspect something. Imagine if we, the inhabitants of a spherical planet, were not three-dimensional, but two-dimensional beings. Then our planet would basically become our universe. And in that case, drawing a small triangle on the ground and measuring the sum of its angles with ordinary instruments, we would get the exact same 180 degrees. But if we drew a triangle of enormous size, then, even with rough instruments, we would find that the sum of the angles was not 180 degrees, but greater. So Gauss hypothesized that our three-dimensional space might have curvature. If so, the sum of the angles of a large enough triangle should be noticeably different from 180 degrees. As far as we know, Gauss measured the triangle formed by 3 mountain peaks in Germany secretly using geodesic measuring devices, and found that the sum of its angles differs from 180 degrees, but differs within the permissible error, so the results cannot be taken into account. He did it secretly for an understandable reason. His colleagues, if they found out that a person is trying in earnest to find the error in the sum of the triangle angles, would have considered that Gauss went crazy. Many years later, Einstein's general theory of relativity was eventually verified by experiments far more accurate than those of Gauss. It turned out that in near-Earth space, the angles of the conventional Great Triangle can total 180.2 degrees. Today, this deviation from Euclidean geometry has to be taken into account, for example, in GPS satellite systems. Hence the question, if such curvature can be detected on the scale of the entire universe, it can give us an idea of its shape. The real shape, not what it seems to us from the inside. And it is curvature that can give us an indication of the universe's closedness. It can be hard to understand how the universe can be closed, with infinity in all directions, but everything becomes clearer if we take the closest analogy to the Earth's surface again. If we start moving in any direction, sooner or later, we will return to the same place. You see what happens? The surface of the Earth has no edge, and yet we realize that it's not infinite. So the universe may be similar, although on a three-dimensional scale. Imagine that the entire space of the universe is twisted into a kind of closed surface like this. You can't imagine it? Don't worry. Practically nobody can imagine it. So we settle for mathematics and vague ideas. And even at this stage of mental experiment, we can come to very unexpected and surprising conclusions, because the closedness of the surface can be different. And now get ready for the unbelievable. Scientists have already done a lot of work on this issue. They have theoretically discovered as many as 18 possible forms, i.e. topologies of the universe, and they are orientable and non-orientable among them. Let us explain what the concept of orientability is. For this purpose, we will consider an interesting two-dimensional surface, a Mobius strip. It can be created from a rectangular strip of paper, twisted once and glued at the ends. Now take point A on the Mobius strip. Draw a normal perpendicular to it, and then draw a small circle around the normal in a counterclockwise direction when looking from the end of the normal. Let's start moving the point together with the normal and the directional circle along the Mobius strip. When the point goes around the entire strip and returns to the initial position, the direction of the normal will be reversed, and the direction of the circle will be opposite. Yes, visually it will be on the other side of the strip, but the surface has no thickness in geometry. Such trajectories are called orientation reversing paths, and surfaces that have them are called non-orientable or one-sided. Surfaces that do not have orientation reversing closed paths, such as a sphere, a torus, and a non-twisted strip, are called orientable or two-sided. So if we assume that our universe is non-orientable, then physically this would mean the following. If we fly from Earth along the orientation reversing closed loop, then we'll certainly return home. But we will find ourselves in a mirror copy of the Earth. We would not notice any changes in ourselves, but in relation to us, the rest of the Earth's inhabitants would have their hearts on the right. All clocks would work counterclockwise, and texts would appear in mirror images. It is unlikely that we live in such a world. Cosmologists believe that if our universe were non-orientable, energy would be radiated from the boundary zones where matter and antimatter interact. However, nothing like this has ever been observed, although it is theoretically conceivable that such zones may exist outside the observable area of the universe. Let's move on. What about the curvature of the universe? Scientists did manage to measure the curvature of space at great distances and found no distortion. That is, the universe is really curved locally near massive objects. But if measured as a whole on large scales, it's flat within the error of measurement, and that points in favor of its infinity. And that leads to some pretty staggering conclusions, one more unbelievable than the other. The theoretical physicist Max Tegmark writes in Our Mathematical Universe that the number of all possible combinations of particles in the observable universe is about 10 to 10 to the 118th power. This is an unimaginably huge number. But if the universe is infinite, that means if you draw a straight line from the Earth in any direction, then after 10 to the 10th to the 118th power of the diameter of the observable universe, that line would meet the exact same Earth with the exact same observable universe where your copy is doing and thinking the exact same thing you are doing at this moment. Well, it's already a bit better than a reversed universe, as in the case of the Mobius universe. But is it really better? It all seems kind of crazy, but there is not a single law of physics that would prohibit such a state of things. In fact, if the universe is truly infinite, it leads to horrific philosophical consequences. Believe me, you wouldn't want to live in an infinite universe. Now, this mental experiment of Max Tegmark is just a walk in the park compared to the absolutely incredible conclusions that follow directly from the assumption that the universe is infinite. The point is that even a completely empty infinite universe only appears to be empty. Ask yourself two questions. The first one, what would happen if you had an infinite amount of time? And the second one, what would happen if you had an infinite amount of space? The answer to both of these questions is everything. Literally everything within the laws of physics. We understand that it sounds implausible, to put it mildly, and not very clear. You'll get it in a moment. An empty universe is never completely empty, because even where there are no particles, there are still quantum fields that are never completely quiet. Quantum fields do not maintain a constant value. and their value at any location in space is always a little bit shaking, trembling. In scientific terms, this shaking is called quantum fluctuations, and they are nothing but consequences of the famous uncertainty principle of Heisenberg. This is not some fantasy. This is modern quantum physics, the most effective model proved experimentally with inconceivable accuracy. And at the quantum level, if we had the ability to wait long enough, from time to time, we would witness really strange things caused by unpredictable fluctuations. In an ever-expanding universe, time and space become so vast that extremely unlikely events can and will happen with 100% probability. You may ask, oh, come on. Are you saying that if you wait even an unimaginably long time, then a piano, for example, can spontaneously appear in a completely empty universe out of nowhere, out of these quantum fluctuations? What nonsense! You may be surprised, but this question was seriously addressed by the most prominent physicist of our time, Anthony Aguirre, Sean M. Carroll, and Matthew C. Johnson. And they even calculated the probability of such an event. If you wait for a period of time a trillion years longer than the age of the universe, you will see this piano appear right before your eyes. Once again, as crazy as this may seem, it is all a direct consequence of the laws of physics at the level scientists understand them today. The less likely an event is to happen, the longer you have to wait. But if you have infinite space or infinite time, and especially if you have both, then any unlikely event will happen an infinite number of times. That's the horror of infinity. In infinite time, it is our universe that will repeat itself sooner or later, with any accuracy. And you will watch this video again, and it will be repeated an infinite number of times. A lot of people won't be happy about that. And a lot of people would prefer the universe to be closed without all those horrible infinities. But there are two things here. First, the universe may still be closed, but simply warped on extremely large scales. And we, like Gauss, may not have the right measuring instruments. So our measurements say that the universe is flat with 99.75% accuracy. That means that if the universe is not flat, it must be at least 400 times the size of the observable universe, 37,200,000,000,000 light years in diameter. And secondly, the universe does not have to be curved in order to be closed. Take, for example, the surface of a cylinder. It is geometrically flat because parallel lines drawn on the surface remain parallel. This is one of the definitions of flatness, and yet it can have infinite dimensions. The same could be true for the universe. It could be perfectly flat, but at the same time still closed. For example, while in a universe that is a four-dimensional sphere, the sum of the triangle angles would be greater than 180 degrees, and parallel lines would intersect. Nothing of this would be true in a universe in the form of a four-dimensional torus. The space will appear flat there. However, moving along a straight line, sooner or later, you will return to the place you came from. In the end, it all comes down to the shape of our universe, a shape that could only be seen by a four-dimensional being. And here we come to a conclusion that will be surprising to many. In conclusion, we will finally explain what was meant at the very beginning of the video about the edge of the universe always in front of our eyes. Let's say more. This edge is not only in front of our eyes, but it is everywhere. We're talking about the fourth spatial dimension. Here's what it looks like. Imagine a conventional two-dimensional world. It can be infinite in all directions, or spherical, or closed toroidal, whatever you prefer. And imagine it contains some two-dimensional matter of its own. There might even be strange two-dimensional beings living there. If we imagine that they have a semblance of our eyesight, the world would look pretty bleak to them. Now let's imagine that this two-dimensional universe is in our three-dimensional universe. What we get is that the whole underside of this world is revealed to us in great detail. Imagine that a two-dimensional world also consists of two-dimensional molecules and atoms. So we, three-dimensional beings, can see every atom of this two-dimensional world as if it was spread before our eyes. And it is crystal clear where the edge of this two-dimensional universe is. Here it is, isn't it? If we make a direct analogy with our three-dimensional world and wonder where the fourth dimension is, the answer is surprising. It is everywhere. Absolutely everywhere. Around every atom. Around every tiny fragment of space. We are literally saturated with this fourth dimension, although we almost cannot interact with it in any way. And it's also true the edge of our universe. So far, the only one we can be confident about.